Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome Daniel van Beck. It's our first time speaker at this seminar, so welcome. I hope not the last one. And he will tell us everything and more about graded, locally finite, and graded just infinite Steinberg algebras. Daniel, it's all yours. Take it away.
Thank you. Thank you very much for giving me the opportunity to speak in the seminar. And yes, I would like to talk about graded locally finite, graded just infinite Steinberg algebras, but I might not be able to tell you everything there is about these algebras, but hopefully a little bit. So I'm interested in group weights and their algebras, specifically Steinberg algebras and C-star algebras. I find the combination of their generality as well as their tractability quite appealing. There are many algebras that we associate with various objects that also have a group weight model. One particular example is that of Levitt path algebras of directed graphs. And so when you get results like these, like in 2008, Abrams, Arandapino, and Silas Molini characterized locally finite and graded just infinite dimensional Levitt path algebras when we view the Levitt path algebra with its natural Z grading. And so the question is then, since Steinberg algebras in some sense generalizes Levitt path algebras, what can we say about these notions for Steinberg algebras with an arbitrary grading, or at least as arbitrary as we can find? And so that's going to be this talk today. I would like to look at those characterizations. And I'm going to start with sort of what I hope is a gentle introduction to ample groupoids and their Steinberg algebras. And those will be accompanied with examples from transformation groups and graphs. And then we'll introduce the notions of locally finite and just infinite and see what that means in the context of group weight algebras, specifically Steinberg algebras. Okay, so to that end, I'm sure many folks here have heard the definition that a group weight is a small category with inverses. I'm going to take a slightly different route and in looking at the axiomatic definition. So toward that end, a group weight is first of all a set G together with a subset of the Cartesian product of G by itself. We call those elements or those pairs composable pairs. So when you compare a group weight and a group, there's essentially two big differences. The one is for a group weight, not all pairs of elements might be composable or multipliable. So the operation is essentially partially defined. And consequently, where a group has a unique identity, a group weight might have multiple identities, as we'll see in a moment. So the set of composable pairs is exactly those elements that those pairs of elements that can be multiplied within a group weight. We need a multiplication map from the composable pairs into G. This is multiplication, composition. We need an inverse map. And all of these sets and maps need to satisfy the following conditions. We would like sort of associativity when it's meaningful for the operation. So if I have, for example, an element gamma eta and another pair eta delta that are composable, then we would like the pair gamma eta and delta to be composable, and we would also like the pair gamma and eta delta to be composable, and then in this case we need the associative property to hold. We would like to be able to compose any element with its inverse, and when we compose elements with their inverses, we would like them to behave as left or right identities, again when multiplication makes sense. Right, so if gamma and eta are composable, then when I multiply gamma on the right by eta inverse, I expect to end up with gamma. So eta inverse acts sort of as a right identity specifically for gamma. And then similarly, gamma inverse gamma should act as a left identity when multiplied on the left of eta. Oh, okay. So groupoids, just set theoretically, are extremely general. In fact, every single set may be viewed as a groupoid by looking at the trivial equivalence relation. And so that's a little bit too general to kind of say much anything interesting. And so we place more structure on the groupoid.
By the way, Daniel, if I might tell you what is the shortest definition of a groupoid, on the level of set theory. It's just a group with an identity crisis.
I like that. I used to call them group wannabes. They want to be
Okay.
groups, but they're not really.
Yeah.
And so we'll work with topological groupoids, and a groupoid is a topological groupoid if the operations multiplication and inversion are continuous. Throughout this talk, at the very minimum, we'll assume that G is a locally compact and Hausdorff groupoid. We'll impose more structure as we go along because we're interested in ample groupoids, but at the very least, all our groupoids are locally compact and Hausdorff. So every groupoid comes with a range map. The range map takes an element gamma and it gives us output gamma, gamma inverse. And sort of analogously, we've got a source map that just sort of reverses the order of that multiplication. So the source of gamma is gamma inverse gamma. And then if we look at the collection of all of the elements of the form gamma, gamma inverse, we call this the unit space. So there's no topology yet. So the space term is not quite adequate, but nonetheless, this is going to be the unit space. So a nice way to visualize groupoid elements is just as arrows. The terminal and the unit space consists of vertices, and groupoid elements consist of arrows between the vertices. And then multiplication. Well, to be able to compose two elements, we need the range of one to be equal to the source of the other. So in this picture, delta is not composable with gamma nor with eta. But gamma and eta are composable since the source of eta is equal to the range of gamma. And then when we multiply, the product we obtain is eta gamma. So you actually read the product from the right-hand side, similar to how you would for composition of functions. So two important structural aspects, we'll consider two important structural aspects of groupoids that will feature later on. The first is that of an isotropy group, sorry. So if you fix any unit U, and you look at all the arrows that start and end at U, so they have range and source equal to U, then all of these groupoid elements form a bona fide group, which we call the isotropy group. And you can sort of see that it's a group because if you run along alpha, then I can run along gamma, and then I can run along beta. So there's really no restriction on how you take these paths. The second important structural property is that of an orbit. So if you fix a unit U, the orbit of U are exactly those units which is connected to U via some arrow. So for instance, in this picture, we have 5 vertices, but U, V, and W are sort of connected via arrows, and X and Y are connected via arrows. So the orbit of U would be the set U, V, W, and the orbit of X would be the set X and Y. Okay, so if your range map is a local homeomorphism, then we call G an étale groupoid. Keep in mind that at this point, we're assuming G has a locally compact Hausdorff topology. Étale groupoids can be sort of viewed as generalizations of discrete groups. And by a local homeomorphism, I mean that every point has an open neighborhood such that the range map restricted to that neighborhood is a homeomorphism onto an open set in G. An open set in the group.
Sorry, Daniel, I always have a stupid question because I keep on forgetting it. So does it imply that also S, the source map, is a local homeomorphism? Okay.
Yes, yes, indeed. You only need to ask for one of them
Yeah. And the
because,
other one follows. Yeah.
yeah, that's right. Inversion is a homeomorphism,
Yes.
so it
Yeah.
follows
Yeah.
from that. And so an open set U is a bisection if the range restricted to U is a homeomorphism onto an open subset.
Mhm.
So if we have an étal groupoid with a base of compact open bisections, then we say the groupoid is ample. And ample groupoids will be the focus of this talk. So let's see what the algebra looks like that we associate with an ample groupoid. So throughout the talk, we'll fix a field K. So I'm not going to bother with indicating over which field we take algebras. The field is K. It can be any field unless we specify otherwise. So the Steinberg algebra, or the groupoid algebra, as Steinberg prefers, is an ample groupoid G. Of an ample groupoid G is the K-linear span of all characteristic functions on compact open bisections. So addition and scalar multiplication is defined pointwise, as usual for functions. And then multiplication is given by convolution. So if I have two functions f and g in the algebra, in AG, and a gamma in G, then the convolution product applied to gamma in that order would be the sum of f of some eta times g of eta inverse times gamma. And we sum over all of those etas for which the range of eta is equal to the range of gamma, so that the variable of g makes sense, so that products are defined within G. Steinberg algebras include the classes of Levitt path algebras, labeled Levitt path algebras, subshift algebras, Kumjian-Pask algebras of higher rank graphs, and Excel-Bardo algebras. There's also a really close connection between inverse semi-group algebras and Steinberg algebras, which we won't explore here. The point is that this is sort of really kind of a general construction, but as you can see by the definition of the Steinberg algebra, that it is fairly tractable in a sense. Working with characteristic functions is kind of nice as functions come and go.
Would you mind giving a simple but not trivial example of such an ample étal groupoid?
Yes, that's the next slide. So in the following slides, I'm going to consider two examples. We'll look at directed graphs and also transformation groups. Okay, so when I say a graph, I mean a directed graph. And when I say a directed graph, I mean a quadruple, where E0 denotes a set of vertices, E1 a set of edges, and R a range map which takes any edge to its terminal vertex. S is a source map that takes any edge to its initial vertex. And then one can build an algebra from a direct graph that in some sense encodes the path structure of the direct graph. These algebras are called Levitt path algebras, and they are the algebraic analogs of graph C-star algebras. The usual way in which a Levitt path algebra is defined is as a free associative algebra that's generated by vertices and edges, And for every edge, you include an extra symbol, E star, called ghost edge, which is the same as E except in an opposite direction. And then subject to these 5 relations. And so I'm not going to go through these relations one by one because I'm not going to use this definition anywhere throughout the talk again, but I would like to just show you how the Levitt path algebra is usually defined. Now, one can realize the Levitt path algebra as a Steinberg algebra of the boundary path group weight E. So let's focus on this boundary path group weight for the moment. And to that end, I'm going to fix a row finite graph. That just means that every vertex emits a finite number of edges. So no vertex can emit infinitely many edges. One doesn't really need this assumption, but for the sake of studying locally finite Levitt path algebras, we're going to end up considering finite graphs in any way, and so there's no harm in just starting off with row finite directed graphs. Excuse me. So a path of length n is a finite sequence of edges such that the range of any sequence is equal to the source of the edge following it in this sequence. We'll let E star denote all finite paths in the graph. We consider vertices as paths of length 0. And then we also have infinite paths, which is just an infinite sequence of edges, again, with the requirement that the range of any one of those edges in the sequence being equal to the source of the following edge in the sequence. We let E infinity denote all infinite paths in the graph. And then this will be an important feature later on. We'll call a finite, we'll call a finite path a cycle if the range of the last edge in the path is equal to the source of the first edge. And no 2 edges in this path have the same source. So essentially you have a closed path, but the closed path doesn't cross itself anywhere. So given a path alpha, then an edge f is an exit for this cycle if the source of f is equal to the range of one of these edges that appear in the cycle, but f is not equal to any one of the edges in the cycle. So you've got the cycle alpha, and then you've got some path leaving the cycle. We call that an exit. For any finite path, x, we're going to let x E1 denote all those edges that are emitted from the range of x. So finite path x, consider its range, and then you look at all the edges that's emitted from the range. That's the set x E1. And so the boundary path space is the collection of all infinite paths on the graph, as well as those finite paths that end in a vertex that emits no edges. Those are so-called sinks. And here too, I know that we call it the boundary path space, but there's no topology yet. There will be a topology, so we'll just stick with the terminology boundary path space for the set. But at the moment, it's just a set. Okay, then we can define the boundary path group weight associated with this graph. As a set, this group weight consists of triples where the first and the third coordinate are boundary paths, and the middle coordinate is some integer that relates these two boundary paths, in the sense that if I chop off enough from the first coordinates path and I chop off enough from the third coordinates path, then I end up with the same path, the x. Right, so if I remove alpha from the first coordinate and beta from the third coordinate, I have x in the first and third coordinates. and the difference of the lengths of alpha and beta determines the integer in the middle coordinate. Multiplication is defined only when the third and first coordinates of the two factors are the same. And in that case, the output is x, the first coordinate of the first factor. We add the two integers, k plus l, and the third coordinate will be the third coordinate of the second factor. Inversion switches the order of x and y and changes the sign of the integer. And so with these operations, GE is a groupoid, which we'll call the graph groupoid or the boundary path groupoid. One can check that if I take the range of an element x, k, y, then I end up with x, 0, x. If I take the source of the same element x, k, y, then I end up with y, 0, y. Which means that all units have the form boundary path element, 0, same boundary path element. And so we identify the unit space of this groupoid with the boundary paths of the graph.
Okay.
At this point, this identification is purely a bijection. Once we introduce a topology, it'll be a homeomorphism. Okay, so let's move on to a topology. We'll first look at a topology on the boundary path space, I beg your pardon, and then on the groupoid. So if we have a finite path mu, the cylinder set of mu consists of all those boundary paths that begin with mu. There's a slightly more general version. If we take a finite set from the edges emitted from the range of mu, then we define the punctured cylinder set as the cylinder set of mu, and we take away all the cylinder sets of mu e, where e is one of those edges emitted from the range of mu. And so here's an example just to sort of maybe give a pictorial idea of what's going on. So there we have a path mu, and the range of mu emits two paths in this instance, x and y. And so the cylinder set of mu would be the two infinite paths starting with mu, namely mu x and mu y. And if we let that set f, the finite set f, let that consist of the very first edge in y, y1. And so then the cylinder set, the punctured cylinder set of mu without y1 would just leave us with the infinite path mu x. Okay, now since our groupoid is defined in terms of the path space, we can use, I should say first that these cylinder and punctured cylinder sets form a basis of compact open sets for a locally compact Hausdorff topology on the boundary path space. Excuse me. And so we can now use these cylinder sets to define a topology on the graph groupoid. And this it's done as follows. So the cylinder sets helps us to define the following. So let Z mu nu denote the set of all triples of the form your first coordinate must be an element of the mu cylinder sets, or something of the form mu x. In the middle coordinate, we have to take off the difference from the length of mu and nu. The third coordinate will be all elements of the form nu x, in other words, elements of the cylinder set of nu. And then the punctured version is very similar, but instead of assuming that mu x is in the cylinder of mu, we now assume that mu x is in the punctured cylinder set of mu for some finite set f. And so these sets form a basis of compact open bisections for a locally compact Hausdorff topology on the graph groupoid. In particular, the graph groupoid is an ample groupoid. And since it's an ample groupoid, we can form the Steinberg algebra by looking at the linear span of characteristics on compact open bisections. And these punctured cylinder or these cylinder sets suffice to that end. Okay. So any questions on this part? All right, then the next example I have in mind is something of a different flavor, in my mind at least. It's that of a transformation group. So suppose you have a group that acts on a set X by bijections. Then we can look at the set of all triples of the form X, G, Y, where X and Y are elements of the set X, and G is an element of the group H. But X and Y are related. X is the action of G on Y. For this set, we can define multiplication similar to the graph case, where we require the middle coordinates to be the same, the Y, Y. And then it collapses. We end up, the product gives us output X in the first coordinate, Z in the third, and in the middle we multiply the group elements to obtain GH. Inversion is very, very similar to the graph case. We reverse the order and take the inverse of the group element G. So with these operations, GXH is a groupoid. The range of any XGY is X identity of HX. The source of XGY is Y identity of HY. And therefore, the unit space consists of elements of the form X identity in HX, and we identify this set with X.
Correct me if I'm wrong, but when X is a principal H bundle, then this transformation groupoid is just the Ehresmann groupoid, right? You don't have to say the element G because the action is free, and when you have X and Y in the same fiber, G is determined.
Yes, that sounds right. I would have to carefully think about it, but it sounds right, yes.
Although
No, it's not true. It's not true.
No, it's not true. Yes, I realize because you have to.
It's an action groupoid.
It's an action groupoid, yes.
Okay.
Yeah. So this groupoid GXH is the so-called action groupoid as well, right?
Okay.
When I started learning, before groupoids, I worked a little bit on cross products for transformation groups, and so then we associated groupoids with these, hence the name transformation groupoids that I often use. But yes, they're action groupoids.
Yeah, I forgot that in Ehresmann you also identify things. There's a quotient groupoid. Yeah.
Okay. So if this group is a locally compact Hausdorff group, and the space X, and if X is a locally compact Hausdorff space, and H acts on X by homeomorphisms, then this is GXH is a topological groupoid considered with the relative product topology. It will be étale if and only if the acting group H is a discrete group. And so étale groupoids actually generalize discrete group actions, not just discrete groups. If we insist that X has a basis of compact open sets, then GXH is an ample groupoid, and its associated Steinberg algebra is once again the span of characteristic functions on compact open bisections. Okay, so these are all that I have in mind for sort of my gentle introduction to groupoids and Steinberg algebras with some examples. So now I'd like to move on to discussing locally finite and just infinite Steinberg algebras. And toward that end, first let's just clarify what we mean by grading. So if A is an algebra over a field K and H is a discrete group, then we'll say that A is H-graded if there exists K linear subspaces of A indexed by the group H, such that we can decompose A into a direct sum of these linear subspaces. And when I take an element of this subspace AG and I multiply it with an element in the subspace AH, then I should get something that belongs to the subspace AGH. We call these subspaces homogeneous components, and the subspace AH is a homogeneous component of degree H. Excuse me. So let G be an ample Hausdorff groupoid, H a discrete group, and let C denote a continuous co-cycle from G into H. So by co-cycle, I mean a homomorphism from the groupoid into the discrete group H. If you look at the identity fiber under the co-cycle, the C inverse of E, then this forms an open subgroupoid of G. And because it's an open subgroupoid of G, it means we can, it'll be an ample open subgroupoid of G. So we can consider its Steinberg algebra, which would be a subalgebra of the Steinberg algebra of G. Now this co-cycle induces an H grading on the Steinberg algebra, where the homogeneous component of degree H would be the K-linear span of all characteristic functions on compact open bisections that are contained in the H fiber of the co-cycle. So you look at the pre-image of H under the co-cycle, you look at the collection of all compact open bisections in that pre-image, and characteristic functions on those, their span would form the linear space AGH. So here's an example. For a directed graph E, there's a natural co-cycle into the integers. The co-cycle just takes an element x, k, y to k. And it is it's fairly well known that for people that work in Leavitt path algebras, that Leavitt path algebras come with a natural z grading, which you can define in a different way by looking at elements and differences of path lengths. But alternatively, you could also arrive at that via the groupoid. Right, so the Leavitt path algebra is isomorphic to the Steinberg algebra of the graph groupoid, which is z-graded. Our second example of transformation groups, if H is a discrete group acting on a locally compact, totally disconnected and Hausdorff space X, then the co-cycle defined by C of X, H, Y projects onto H is again a co-cycle, and so the Steinberg algebra of the transformation groupoid, that should be AGXH at the bottom, there's a typo. The Steinberg algebra of the transformation groupoid is then H-graded. Okay, so for the remainder of this talk, until we arrive at applications, let's fix an ample groupoid G, a discrete group H, and a continuous co-cycle from G into H. Excuse me. So then, as we just explained in the previous slide, this co-cycle induces a grading on the Steinberg algebra. And so we'll say that the Steinberg algebra with this grading is locally finite if each homogeneous component is a finite dimensional K vector space. Right, so you've got this decomposition into linear subspaces, and local finiteness means each of these linear subspaces must be finite dimensional. And I just want to highlight something here. For the remainder of the talk, I'll just refer to algebras being locally finite, but do take care that this local finiteness is for some grading on an algebra. The notion of local finiteness obviously appears in many areas of math. You get something like locally finite groups, locally finite inverse semigroups, etc. This local finiteness is particular for the grading that we place on the algebra. So, what do we know about local finiteness for Leavitt path algebras? Well, before we get to that, I'd like to highlight an interesting feature about about Leavitt path algebras with the natural Z grading. So Abrams, Aranda-Pino, and Silas Molina in 2008 proved the following. Assume that E is a finite graph, then the following are equivalent. If one of the components, the homogeneous components in the grading, is infinite dimensional, then all of the components in the grading are infinite dimensional, if and only if E has a cycle with an exit. And a note on the finiteness of the graph, it is crucial in this theorem. If you remove the finiteness of the graph, then this theorem no longer holds. And the authors give an example of that in their paper.
May I make a quick topological comment? You
Yes.
see, this grading comes from the gauge action, the circle action on the graph C-star algebra of this Leavitt path algebra. And when these elements with a subscript n, these are just associated line bundles, or if you're on module of section associated line bundles. So it has a very nice topological meaning. And in particular, you can take a finite graph of, say, quantum sphere, any Waxman-Soberman quantum sphere. You have a very nice finite graph. So in particular, rho finite. All the assumptions are satisfied. You have your gauge action, which corresponds exactly to the usual action of U1 on an ortho-dimensional sphere. And when you take the quotient, you get quantum complex projective spaces of Waxman-Soberman. So this has quite nice topological meaning, and it's all there. This is your algebraic backbone.
No, that's very interesting. Yeah, I mean, so C-star algebras are often called what non-commutative topology, so kind of makes sense. Yeah, so and so, like I said, the finiteness of the graph here really is essential. And then of course we're interested in ample groupoids. So do we have an analog of this result for Steinberg algebras? We do, but not in the generality that Abrams et al. Proved. So if we assume that that if you take any H in the image of the cocycle and you look at its pre-image in the group weight, the H fiber, if the source maps that fiber onto the unit space, then one homogeneous component is infinite dimensional if and only if all of them are infinite dimensional. So in some sense, you would like the group weights elements to be spread out in a nice enough way so that when you take the source of any of the fibers under the cocycle, you get the whole unit space back. Okay. Yes.
Well, I have a question. Is there some analog of a cycle in this situation?
Not that I'm aware of, no. And that was one of sort of the hard things to try and find a generalization or analog of their result. So the first thing is the cycle part. And the other thing is that this result, they work with, Abrams, Pino, and Molina work with Leavitt path algebra specifically with the Z grading. And that has very particular properties that arbitrary gradings on Steinberg algebras don't have. So those were two sort of obstacles to try and overcome is this, the missing notion of a cycle, and also that we don't necessarily have a Z grading that linear path algebras come with.
Okay, thank you.
Okay, and so Abrams, Arandapino, and Silis Molina also proved the following characterization. Well, first, sorry, before we get there, they also proved that if the Levitt path algebra is locally finite, then the graph E must be finite. And which is why earlier I assumed row finiteness, because eventually we're going to talk about finite graphs anyway. So this notion of local finiteness is fairly restrictive. Okay, so they have the following characterization for locally finite Levitt path algebras with the Z grading. The algebra is locally finite if and only if no cycle in E has an exit. Okay, so natural question, can we generalize this to Steinberg algebras with A grading? And to sort of try and create some intuition for where our characterization comes from, I'd like to just analyze this no cycle in E has an exit statement that appears in their theorem. Right, so for example, what happens if a cycle has an exit? So here's a cycle alpha, and then we have an edge E that's an exit. So that means you can run along alpha as many times as you like, and when you get tired of alpha, you could always exit alpha by taking E, right?
Yeah.
And so what happens here? Well, if you take two natural numbers that are distinct, then first of all, if you look at the cylinder set of alpha M, right? So remember, the cylinder set are all of those boundary paths that begin with alpha M. All right, so now if I run along alpha M times, then I have two options. Either I can run along alpha some more and then exit, or I can just stay in alpha. So the cylinder set has two elements. No, sorry, not two elements. It has infinitely many elements. It has alpha infinity, just the infinite path consisting of alpha, 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 and so on. Or I can do alpha M times and then another K times, and then exit with E, where K represents some natural number. And so this is an infinite set, right? And also note that if M is not equal to N, then the cylinder set of alpha ME and the cylinder set of alpha NE are disjoint. Right? There's no way that I can get an infinite path that starts both with alpha M and with alpha N. Alpha ME and alpha NE. For instance, if alpha M is less than N, then the first one tells me I must take the M cycles and then I need to exit. But that doesn't allow me to do the remainder of the N cycles. And so these are disjoint. Now, remember that the boundary path space is homeomorphic to the unit space of the boundary path groupoid. These cylinder sets form a basis of compact open sets for the topology on the boundary path space. And since these Z alpha ME and Z alpha NEs are all disjoint for M and N distinct, it follows that the characteristic functions on them are linearly independent in the Steinberg algebra of the unit space groupoid. But the Steinberg algebra of the unit space is contained in the Steinberg algebra of the zero fiber under the cocycle. In other words, the zero component in the grading. And so it follows that the dimension of the zero component must be infinite, right? Because I have infinitely many linearly independent elements in that set. And so there's no hope for this Levitt path algebra to be locally finite because the zero component is infinite dimensional, all because the cycle has an exit. Okay.
By the way, maybe it's also worth observing that in this particular case, this grading that you have over here, it's not strong. I mean, it is graded, but not strongly
Ah,
graded.
yes, so that you have a proper inclusion.
Yeah.
Yes. Yeah. Okay. And how about if there aren't any exits? So here is pretty much the same graph, except we change the direction of E. Right? So if I now run along E and then I get into alpha, then I'm stuck in the cycle alpha for all perpetuity. There's no getting out. Right? And so in this case, for all n, the cylinder set of alpha is equal to the cylinder set of alpha n, which is just the singleton alpha infinity. And so this tells me that this singleton is an isolated point. It's an open set. The same argument applies to the cylinder sets of E alpha n, or just E alpha. That'll have the singleton E alpha infinity, which is also an isolated point. And so the boundary path space for this particular graph consists of alpha infinity and E alpha infinity, both of which are isolated. And so the boundary path space is discrete. But the boundary path space is the unit space of the graph groupoid. If it is discrete and the groupoid is a tall, then the groupoid itself must be discrete. And thus, the characteristic functions on singletons coming from the K fiber of the cocycle would form a basis for the homogeneous component of degree K. In particular, if the K fiber in the groupoid is infinite cardinality, then the K homogeneous component would be infinite dimensional. And this is sort of our key to the groupoid characterization. This is what this proposition essentially tells us, right? So if the dimension...
If you
Hello?
don't mind going back to the previous slide for a second,
Sure.
you see it's very easy to see it from the point of view of noncommutative topology because we know these sister algebras, they are old friends. So here we have 2 by 2 matrices over the circle. In the previous case, this is the Teplitz sister algebra. If you look
Yes.
at the Teplitz sister algebra and view it as Coburn, as the universal sister algebra generated by one isometry, it's pretty clear that a linear basis that you have is of the form isometry S to N times its adjoint S star to another K, whatever. And then
Right.
your grading is by the difference of these two numbers. And it's obvious
Yes.
that you can have infinitely many natural numbers that differ by the same number. And so the dimension is infinite. On the other hand, if you look at things that happen over the circle, well, I mean, you always have just things are one-dimensional because you take your unitary in some power and that's it. And this is your grade. And then if you go to 2 by 2 matrices over this, it's just Morita equivalent. You don't change much.
Right.
So this is
Yes.
why I if you ask me to guess it like this, which one is which, I would immediately say it's because of
Yes.
that interpretation, it must be as you say it.
Right. Right. And I mean, so this discrete observation and the basis due to this discreteness is kind of key for us to extend to Steinberg algebras with gradings other than say a Z grading, right?
Yeah.
So I think the examples you mentioned still requires the Z grading.
It's Z grading, yes, because it all comes from the gauge action. Yeah.
Right. Okay, so and then due to sort of that argument from the previous slide, the homogeneous component of degree H will be finite dimensional if and only if the H fiber in the groupoid is finite. And in this case, singletons or characteristic functions on singletons in that fiber would form a basis for the homogeneous component of degree H. Okay, so and then we have our characterization for locally finite Steinberg algebras for a particular cocycle or grading. It is locally finite if and only if every one of your, excuse me, if every one of your fibers under the co-cycle is finite in cardinality. Okay, so here's a consequence of this. If we suppose that the Steinberg algebra is locally finite, then the group weight must have finitely many orbits, each of which is itself finite, and we can decompose the Steinberg algebra into a finite direct sum over matrix algebras, where the entries of each matrix algebra are isotropy group algebra elements. So the group algebra of your isotropy group coming from a particular one of these finite orbits form the entries for these matrix algebras or these matrices. Okay, so what does being locally finite mean for representations of Steinberg algebras, in particular irreducible representations? Here I'm specifically interested in a property called CCR. And so we're going to define a K algebra A to be CCR if all of its irreducible representations over K act by finite rank operators, so matrices. The notion of CCR dates back to work of Erwin Kaplansky, I believe possibly in the 1950s. He defined these notions also for C-star algebras, where C-star algebra CCR, if and only for every irreducible representation, you map onto compacts. And initially, he defined CCR in an algebraic sense in terms of minimal left ideals having some properties. Together with Ben Steinberg and Lisa Clark, we looked at these properties for Steinberg algebras, and you can equivalently, in some instances, define them as those algebras for which the irreducible representations act by finite rank operators, which brings it sort of in line with the notions from C-star world. So Lisa, Ben, and I proved the following theorem. And first, there's an assumption that we need to make. We need to assume that the field K is algebraically closed and the dimension of the algebra is less than the cardinality of the field. This is to ensure that the spectrum is non-empty. So this is sort of something we have to deal with. But if your group weight, for instance, is second countable, then your Steinberg algebra would be of countable dimension. And if the field K is the complex numbers, then this property is satisfied. So then sorry, is there a question?
No, I was clearing my throat, sorry.
Oh, okay. So the Steinberg algebra is then CCR if and only if all the isotropy group algebras are CCR and if all the orbits are closed in the unit space. In particular, if the group weight has virtually abelian isotropy, then the isotropy group algebras are automatically CCR. Then the Steinberg algebra is CCR if and only if all orbits are closed. And so then we get, maybe let me just show you. So if you look at this corollary at the bottom, if the algebra is locally finite, it has a finite number of finite orbits. And so the space is Hausdorff, which means singletons are closed. And so each orbit is a finite union of closed sets and therefore closed. And so we then immediately get the following result for locally finite Steinberg algebras. If it is locally finite with respect to some co-cycle, then the algebra is CCR. So all irreducible representations act by finite operators, finite rank operators. Okay, so I'm going to end here with locally finite and move on to the next property that we're interested in. We'll split this up into two. There's just infinite and then there's graded just infinite. So we'll call a Steinberg algebra just infinite. It's actually meant to be just infinite dimensional, but it's been sort of shortened to just infinite. So the Steinberg algebra is just infinite if it is of infinite dimension, but the quotient by any ideal, non-zero ideal, is finite dimensional. Okay, so an ideal is graded if we can express it as the intersection of the homogeneous components direct sum. And then we'll call a graded just infinite if the Steinberg algebra is of infinite dimension, but the quotients by graded ideals are finite dimensional for every non-zero graded ideal. And of course, just infinite implies graded just infinite. The converse fails in general, even for Levitt path algebras. Silis Molina and et al. Gave an example in their paper to illustrate this. Okay, so since we're interested in ideals, we need to speak about ideals coming from open invariant sets in groupoids. So an open set in the unit space of a groupoid is invariant if the range of the pre-image of the source of U is U itself. Alternatively, if the source of an element is in U, then the range of the element must also be in U. If U is invariant and either open or closed, then the reduction to U is an ample subgroupoid of G. If U is open invariant, then its relative complement in the unit space is closed invariant, and the Steinberg algebra of the reduction to U is a two-sided ideal in the Steinberg algebra, such that if we quotient by that ideal, we get the Steinberg algebra of the reduction to W. Right, so essentially we have a short exact sequence. And so given this, if the Steinberg algebra is just infinite, then we should have that all quotients by ideals must be finite dimensional. In particular, the dimension of the Steinberg algebra of this G reduced, the reduction of G to W must be finite dimension. Oh, sorry. And so we immediately almost get the following. Well, sorry, let me just backtrack for a moment. So we're going to be interested in knowing when the dimension of such reductions are finite dimensional. In particular, when is a Steinberg algebra finite dimensional? And the Steinberg algebra is finite dimensional if and only if the groupoid is finite. One can see this by noting that if the Steinberg algebra is finite dimensional and you consider the trivial grading, together with a local finiteness characterization, implies that G must be finite. Alternatively, if G is finite and the fact that G is Hausdorff implies that G is discrete, and therefore characteristic functions on singletons will form a basis for the Steinberg algebra. Okay, and so we get sort of a partial characterization for just infinite Steinberg algebras. If the Steinberg algebra is just infinite, then the reduction to any non-empty, closed, invariant, and proper subset of the unit space must be a finite groupoid. This follows directly from this short exact sequence argument, as well as the lemma above. Also, if you have a unit and its orbit is not dense in the unit space, then the isotropic group is finite. And consequently, all orbits are either dense or finite. Right, so next we would like to consider, we'd like to consider sort of graded just infinite Steinberg algebras. And one reason is that in this proposition, to try and get a converse of, say, the first item, one would need to get a handle on all ideals in a Steinberg algebra so that you can consider quotients and their dimensions. I'm not aware of a nice characterization of all ideals in a Steinberg algebra, but we do know a lot more about the graded ideals in a Steinberg algebra. And so to that end, we introduced the notion of strongly effective. So first of all, the isotropy bundle of G consists of all the elements that come from isotropy groups. So all elements with range and source equal. Then we'll say G is effective if the interior of the isotropy group is precisely the unit space. We'll say that G is strongly effective if the reduction to every closed invariant subset W is a strongly effective, is an effective groupoid. Right, so let me say that again. Effective if the interior of the isotropy group is the full unit space. Strongly effective means that should hold for all reductions to closed invariant subsets of the unit space. So in 2018, Lisa Clark, Rui Excel, and Enrique Pardo proved this awesome theorem. I really like this. They showed that if the unit fiber under a cocycle is strongly effective, then there is a lattice isomorphism from the open invariant sets in the unit space onto the graded ideals of the Steinberg algebra. And so with this theorem, we have a grip on all the graded ideals, which allows us to say a little bit more about graded just infinite Steinberg algebras. Excuse me. And so this is our characterization for graded just infinite. Suppose G is an infinite ample Hausdorff groupoid and that the identity fiber under the cocycle is strongly effective. Then the Steinberg algebra is graded just infinite if and only if the reduction to every proper closed invariant subset of the unit space gives you a finite groupoid.
Sorry, could you for a second go back to the previous slide?
Sure.
And this question is more for Tomek Maszczyk than for you, but let me say it now before I forget it.
Sure.
You see, there is a very similar lattice isomorphism in case of Hopf-Galois theory. Then the Galois condition ensures that there's a lattice isomorphism between equivariant ideals in the comodular algebra and ideals in the fixed point subalgebra. It is a lattice isomorphism. And this is what you can explicitly write down, this lattice isomorphism using a strong connection, if I remember correctly. So Tomek, do you think there's any connection between this Galois theory effect and what we have here?
Well, probably there is a connection for this action groupoid. But I'm not sure. I'm not sure what is this connection.
Yeah. Okay. So, sorry, it was just a very loose association, but it's kind of, really on the surface very similar because A, it's a lattice isomorphism, and B, on one hand side, you compare some objects which are in a bigger structure but have some properties with all objects in a smaller structure.
No. So for what it's worth, if you don't consider Steinberg algebras, if you look at C-star algebras of Vital groupoids, for instance, I'm not aware of an analogous result to this for Vital groupoid C-star algebras, but it's something that I've been working on, and I think I might have an analog of this theorem. The thing is that for Steinberg algebras, they use this sort of ample structure of the groupoid quite explicitly in their proof, which isn't available for Ital groupoids, right? And so there I had to use quite different techniques to try and get this. And there it sort of amounts to something similar to what you said, at least it smells similar, in that the open invariant sets, there's a lattice bijection between that and action invariant ideals where the action comes from a co-cycle.
Yeah. Okay. Okay. Thank you, sir, for the interruption.
Yeah, no worries. Okay, so this is the characterization of graded just infinite Steinberg algebras. So I would like to mention something. This property that we require the unit fiber to be strongly effective. I don't know about other folks, but to me it feels like it's sort of a relatively hard and abstract property to test and check, because you want to look, according to the definition, you want to see if the interior of the isotropy group bundle is the same as the unit space. So it can be hard to check, but it turns out that many group weights actually have this property, many ample group weights. And one can see this with the following result, right? So if your co-cycle restricted to isotropy groups is injective, then the unit fiber is a principal group weight, and in particular, it would then be strongly effective. And so if you look at the examples we considered a little bit earlier, you have a graph group weight. Isotropy group elements are all of the form x, k, x for some integer k. And the way this co-cycle is defined by taking the projection onto the middle coordinate is injective when restricted to isotropic groups, and therefore the unit fiber is strongly effective. So in the same paper by Clark, Excel, and Bardot. Where did I've lost it. I'm sorry. No, there it is. In the same paper of Excel, Clark, and Bardot, they show that for Boolean dynamical systems, you always have a principal unit fiber, but it turns out that it works in greater generality. So here for graphs, we see it. That follows from their Boolean dynamical system arguments as well. But also for transformation groups, right? So if you look at the natural co-cycle that we introduced a little bit earlier, here too, your isotropy group elements would be of the form X, group element X. Co-cycle takes that to the group element, and so it's injective on isotropy groups, and therefore the identity fiber is strongly effective. And so even though this assumption C, the unit fiber being strongly effective, seems sort of awkward to work with, at least for me, it turns out that many group weights, ample group weights, have this property. Okay. So what can we say about the representations of the irreducible representations of just infinite Steinberg algebras? Again, we need those assumptions that the field's cardinality is greater than the dimension of the Steinberg algebra. But in this instance, we're also going to assume that the group weight is either transitive or has no dense orbits. And then, if the Steinberg algebra is just infinite, then it is CCR. And it turns out that those assumptions of being transitive or have no dense orbits for AG to be CCR cannot be removed. As soon as you remove those, you end up with with Steinberg algebras that are no longer CCR. So I didn't include an example here for the sake of time, but we do have an example that illustrates that. Okay, so in the Levitt path algebra case, Abrams, Aranda-Pino, and Silas Molina proved that if you have a directed graph such that the Levitt path algebra is infinite dimensional, then it is graded just infinite if and only if it is graded simple. This result fails for Steinberg algebras in general, but we can find an analog by introducing the following property. So we'll say that G satisfies property FIC. It's meant to allude to finite invariant closed if you're given some non-empty invariant subset of the unit space such that the such that the restricted group weight is finite, then the set W must be Clopen. And then we can say the following. If we have a strongly effective unit fiber, the group weight satisfies this property FIC, and the Steinberg algebra is infinite dimensional, then it is graded just infinite if and only if it is graded simple. Okay, so what happens if we combine local finiteness and just infinite? So the first thing we sort of observe is that if the Steinberg algebra is both locally finite and just infinite, then the group weight must be transitive. So this is severely restrictive, right? Moreover, the Steinberg algebra is isomorphic to a matrix algebra of that form. Entries with coming from the group algebra of one of the isotropy groups. And you can take any one of the isotropy groups because they're all isomorphic if the group weight is transitive. All right, and then we have the following characterization. So again, if the unit fiber is strongly effective and the Steinberg algebra is locally finite and infinite dimensional, then the following statements are all equivalent. So Steinberg algebra is graded just infinite if and only if it is graded simple, if and only if it is transitive. And if we place the Z, if the Steinberg algebra has a Z grading on it, then all three of those statements are equivalent to the Steinberg algebra being just infinite. So initially, I thought it would be interesting to see if one can take the proposition above for the first two items only and remove graded. So would this context have just infinite equivalent to simple? And it turns out that that is never ever the case, because if the Steinberg algebra is locally finite, then the group weight is discrete. If it's infinite, if it's just infinite, then it is transitive. And so up to isomorphism, there's only one isotropy group. This isotropy group must be infinite and discrete, and therefore the interior of the isotropy group bundle will not be the unit space. And so you never ever get that. So the group weight is minimal, but never ever effective. Okay, so I have a little bit of time left. I would like to look at one application. I initially thought that I would look at two applications, Deacon-Renault group weights as well as group weights coming from shift spaces, but I opted to only talk about the Deacon-Renault group weights for sake of time. But we do consider group weights of shift spaces as well, and find various characterizations for those. So let X be a locally compact Hausdorff and totally disconnected space. Let sigma be an action of the natural numbers on X by local homeomorphisms. Then we call the pair X sigma a Deacon-Renault system, and the group weight of the form consisting of all triples of the form X and Y in the first and third coordinates coming from X, and in the middle we have the difference of two integers, where if I apply sigma m times to X, that should be the same as applying sigma n times to Y. And so with the specific, the operations look very similar to those for the transformation groups and for graph group weights. In fact, graph group weights are examples of Deacon-Renault group weights. So with the specific topology, analogous to the graph case, G X sigma is a Deacon-Renault group weight, which also has a canonical co-cycle into the integers, as we saw with graphs. You'll note that C restricted to each isotropy group is injective, And therefore, the zero fiber is always principal and thus strongly effective for ample Deacon-Renaud group weights. Deacon-Renaud group weights include many classes, including graph group weights, label space group weights, higher rank graph group weights, subshift group weights of Boava et al., and more. Right, so here is our characterization of locally finite Deacon-Renaud systems, or I should rather say locally finite Steinberg algebras of Deacon-Renaud group weights. The Steinberg algebra is locally finite if and only if the set X is finite. And it turns out this is equivalent to the Steinberg algebra having or being no ether. So it has the ascending chain property. For greater just infinite, if the Steinberg algebra of the Deacon-Renaud group weight is infinite dimensional, then it is greater just infinite if and only if for any proper non-empty closed set in X, which is invariant under both sigma and sigma inverse, the space W must be finite, and the domain of the map sigma restricted to W applied the cardinality of W times must be empty, must have empty domain. So at some point, if you keep applying this map sigma restricted to W, you're going to end up with an empty set. Sorry. Okay. And finally, I have two more results that I would like to share. So if you suppose that the points outside the domain of the map sigma are all isolated, for instance, if the domain is all of X, then the Deacon-Renaud group weight satisfies this property if IC, finite invariant closed. And therefore, we obtain the following. So if the Steinberg algebra is infinite dimensional and the points outside of the domain of sigma are all isolated, then if we consider the Steinberg algebra of this Deacon-Renaud group weight with the natural Z grading, then it is graded just infinite if and only if it's graded simple, if and only if the group weight is minimal. And that is where I'm going to stop. Thank you very much. I guess I'm a little bit early, but yeah. At least I
Thank you
finished.
very much indeed. So we have plenty of time for questions. We still have 13 minutes, so we should. Now it's, not only an ample groupoid, but an ample amount of time for you to
That's right.
to go to some other places. So my first theme that I would like to explore is kind of obvious. Okay, Tomek has a question. Okay, so maybe Tomek first. Go ahead, Tomek.
Okay, so I have a question about this cocycle generating this grading of a Steinberg algebra. If you have two cocycles which are cohomologous, what can be said about these gradings? Can they be compared somehow?
My honest answer is that I don't know. I unfortunately, for this question, I do not know a lot about homology and cohomology. And so when I, for the sake of this work, work with cocycles, I do not necessarily have cohomology in mind. I sort of view it as a homomorphism from the group into the discrete group. And with that property, or just the cocycle identity, you can sort of proceed with the construction without having to factor in the fact that this cocycle actually comes from other structures as well. It has other connections as well. So honest answer, I unfortunately don't know.
It's a pity because I had a series of such questions, how this cohomology can affect all these properties
Yes.
of this fiber of this cocycle and so on and so forth. But this is,
that might be interesting to explore. What I can tell you though is that obtaining a grading via a co-cycle in this fashion or in a similar fashion isn't unique to ample group weights. Astrid and
Yes.
Hoof and some other folks have done it for locally compact, second countable Hausdorff group weights with a Haar system as well. Then they find a topological grading in the sense of Rui Excel for the group weight C-star algebra. So I guess your question would then also apply to a much larger class of group weights. Yeah.
Okay, thank you.
But can we dig in a little bit deeper into Tomek's question? So could you first remind me the definition of a cocycle and what exactly, Tomek, you mean by equivalence in the cohomological sense? What is close? What is exact?
Okay, so if you have a cocycle, you have a multiplicative map from arrows to a group.
Okay, so
And then you
cocycle is
can,
just a multiplicative map
yeah,
from arrows into the group, right? That's your cocycle. Okay, good.
yes. So, but G is a groupoid.
Yes.
So every arrow here has two ends,
Yes.
and you can twist such a cocycle by a map from units of this groupoid to the group H itself.
Aha.
And you can twist from the left, and you can apply the inverse twist from the right.
All right.
Okay.
Uh-huh.
This is sometimes called gauge action.
Okay.
Okay. So my general question is how much all these properties of different aspects of Steinberg algebras, how are they gauge sensitive?
Mhm. Okay. Now I understand your question really. Okay. So for you, cohomologous is in a sense gauge equivalent.
Yes, gauge equivalent. Yes.
Okay. But you multiply it as on one side. It's not like a conjugation on both sides.
No, from both sides.
Aha.
Because if you have x and y, you can have some function evaluated at x and multiplied from the left. And the same function could be evaluated at y, at the opposite endpoint, and multiplied from the right with the inverse.
Okay.
Okay, so this is gauge equivalence of cocycles.
Okay.
If they are non-abelian, if they are abelian, if H is a abelian group, like for graph or Levi's path algebras, then it's usual cohomology from homological algebra.
Okay.
I think it's an interesting question.
Do you expect it to work out much nicer in the case that H is abelian?
Yes, because if H is abelian, it's something which is in the scope of a usual homological algebra. It's a part of homology theory. If H is non-commutative, non-abelian, if H is non-abelian, then the first cohomology is only a set, a pointed set. So there is no continuation to some homological algebra, higher homological algebra. There are some special cases like gerbs, but it's a different question then.
Well, and since you mentioned that you like cross products, let me recall that there's a very beautiful effect in the spirit of what Tomek is saying, exactly with cross products, because if you have a cocycle cross product, and the only difference is that the cocycles are cohomologous, then you have an isomorphic algebra. And that's very important because you might have seemingly different presentations. You might look, oh my goodness, what a monster it is. But then you choose a cohomologous cocycle and you see that it's a pretty nice, cool algebra, which looked monstrous in other presentation. So that's not just a random question. I agree with Tomek. It's a good question. Tomek, do you want to continue?
No, thank you.
Okay. So my obvious question, a question I cannot refuse, is the following. When you take our most beloved Levitt-Pav algebras and you decide that your ground field is complex numbers, then you can just take the universal enveloping sister algebra and everybody is happy. We have graph sister algebras. But how about your Steinberg algebras? Say that we are happy with a field of complex numbers. Can I then take the universal sister algebra? Does those exist? Does it have some properties? I mean, examples that you gave as examples of Steinberg algebras enjoy this property, Comjian Pask and so on. But how about in full generality? Take absolutely arbitrary Steinberg algebra over complex numbers. Does it enjoy the universal sister envelope?
I think so, but I am not 100% sure. There's a paper by Lisa Clark and I think perhaps Aidan Sims and one or two more authors where they show that you can densely embed a Steinberg algebra over the complex numbers into the group weight C-star algebra.
Aha, okay. But it's
So,
just an embedding. You don't say that it's a universal envelope.
right. But I think that might be an avenue if you wanted to know.
Yeah, if you can embed it, then I guess the universal should exist. But okay,
right.
Okay. Because in the Levitt case, this is extremely regular because the Levitt-Pav algebra is actually nicely embedded in its sister algebra. It's kind of, I like this analogy. If you take, say, a group ring, and if your group is amenable, then taking the reduced group sister algebra or the universal one is one and the same thing. So by this analogy, Levitt-Pav algebras are kind of like amenable group rings.
Yes.
They are very regular and really have embedding, and which is very nice.
Yes. I'm not, as I say, I don't remember the exact details of that paper, but I think they embedded densely into the maximal C-star algebra, not the reduced gadget. Of course, if G is amenable, as you said, then same algebra, but yeah, so I don't know the exact details, but I think they embedded into the full C-star algebra.
Okay, another thing which comes to my mind, because I had a funny adventure with Steinberg algebra, kind of unwanted. And we were looking at the criterion for the grading, or if you want gauge action to be free, gauge action being free or the grading being strong, that's equivalent. Okay. And we developed this. We managed to find a criterion. We worked on it with Mariusz Tobolski and Soren Elias and Alexandru Kirvasitu, and where we got our result, and we were typing a paper. Alexandru went to a conference, and somewhere he met some people, and they alerted him to a work of, I'm sure it was Lisa and a bunch of other people, whom I don't remember, just remember Lisa, about Steinberg algebras, where actually there is a criterion for the freeness of the action, or if you want, strongness of the grading, okay? And when Levitt-Pav algebras come as a special case, so we had to abandon the paper. It was useless because it was just a special case of somebody else's work. But I would still appreciate if you would remind me what this criterion was. Imagine that I have a Steinberg algebra and it is graded. And what is the criterion for this to be strongly graded?
I know the paper you're referring to.
Okay.
I don't have the result off the top of my head, so I can't comment on the exact criteria, but I know the paper you speak of. What would that be? I don't know. Is it? No, I'm unsure. I'd rather not
Okay.
not speculate.
Because
Uh,
the grass Hester algebras or Leibniz algebras, that's the same thing here, the same effect. I remember that sinks were some troublemakers. Yeah. That's why when you showed me the Steplitz graph, okay, I told you it was not strongly graded, and
right.
in fact the gauge action is not free in the usual Sister algebraic sense of Elwood. Uh,
So
but
if
what is a funny purely quantum effect? You see, in classical topology, when you have a contractible space, you cannot have a free action of a finite group, right? You'll always have a fixed point. So
Mhm.
if you take a unit disk and any compact, not necessarily finite, you cannot have a compact group acting freely on this. So this includes finite groups, but with a Teplitz sister algebra, you have a funny effect. I mean, the gauge action is not free, but if you take any cyclic subgroup of your circle group, any Zn, then its action is free, which is impossible classically.
Mm.
But it's no longer a
Yeah.
gauge action. It's no longer this full grading. It's kind of you turn your full Z grading into a finite cyclic grading, and then it is strongly graded. Okay, Tomek, you have a question.
Can I just offer two comments on that? Sorry, Tomek.
Okay, yeah, go ahead. Yeah, sorry, you first. Sorry, yes.
Yeah, so you mentioned that sort of the freeness of the action, right? So if you look at the transformation group weight, freeness of the action implies the group weight is principal,
Okay.
right?
Yeah.
So you have
Yeah.
trivial isotropy groups.
Yes.
And then you also mentioned that somehow the presence of sinks in the graph
Yes.
poses problems, right? And
Yes.
so for what it's worth, in the group weight version, that would translate to isolated points in the unit space,
Okay.
because sinks in the boundary path space are
Yes.
isolated. Yeah.
Yes.
So I don't know if that is any
No,
help
no, no. It's fully
whatsoever,
related. Yes.
but I would start with those. Yeah.
Yeah. Tomek?
Sorry, Tamak. Yeah.
No, no. This is
So my next question is about the relation between this purely algebraic approach and the Renault program of modeling sister algebras. So it is based on the notion of Cartan subalgebra
Mhm.
and all this stuff. So can you draw some analogies between these pure Steinberg algebras and kind of purely algebraic Renault program?
Um, Not at the moment, but it is something that is in the back of my mind as a follow-up to this project. Again, this is some area that I would like to learn about a little bit more, is the connection between cocycles and twisted group weight algebras, and whether one can find an algebraic analog of that. I'm not sure. Oh no, Becky Armstrong, Lisa Clark, and I think perhaps Astrid and have had a paper on twisted sign Steinberg algebras. So there must be some algebraic version of the twisted gadgets, which is, I think, the same gadgets that Renault considers, right, for principal group weights and the existence of these Cartan pairs. And so what exactly the connection is between the twisted uh, Steinberg algebras, the work we do here, and then also an algebraic analog of the Cartan pairs. I'm not sure what it is or if there is something, but I know about the cocycles have a close connection to twisted algebras, and so it seems like a natural avenue to explore after this project.
So my question had nothing to do with cocycles this time.
Sorry,
Mhm. Mhm.
So
then I
this
misunderstood. I'm sorry.
no. It was about maximal commutative subalgebras, Cartan subalgebras, rather.
Mhm. Well, so the point that I'm trying to make, I think, is that if I remember correctly, so Renault's theorem for principal group weights says that if the group weight C star algebra has a Cartan pair, then you can, oh, sorry, if the algebra as a Cartan pair, then you can realize it as the C-star algebra of a twisted groupoid. And these twists often come from co-cycles. Or you can
Is there an analog of the Cartan pair?
In the algebraic sense, I do
Steinberg
not.
algebras? No.
I do not know, unfortunately.
Okay. Thank you.
Yeah. So yeah, sorry. So I guess I went off on a little bit of a rant, but there is some connection toward co-cycles if you push it far enough, because the realization of an algebra with a Cartan subpair as a twisted groupoid C-star algebra means the groupoid somehow has a twist, a co-cycle defined with it.
Okay, are there any further questions? Adam?
No, I'm happy. Thank you.
Quiet today. All right. So in this case, let us thank our speaker again. Thank you so much.
Thank you.
Thank you for having me.
Let me stop recording.